Hi, I'm Daphna Idelson from GSI Technology, and I will be giving an introduction to our work, Hamming Space Locality Preserving Neural Hashing for Similarity Search. Finding the most similar items in a database to a query is a fundamental task in information retrieval. It can be found in many real-world content search applications, such as visual search, face recognition, text search, and recommendation systems. The k-nearest neighbor algorithm searches the database by retrieving the k closest items represented by points in a d-dimensional feature space, a representation commonly performed using machine learning methods. As databases become increasingly large and the search computationally challenging, approximated KNN algorithms are needed. One such group of algorithms is binary hashing, a mapping of feature vectors to locally sensitive compact binary codes, allowing efficient distance computation. In this work, we present an unsupervised data-dependent method for learning a simple and effective binary hashing network. Let me start by describing the model architecture. The feature vectors first pass through several fully connected neural layers, usually one or two such layers. Then, through a final fully connected layer that normalizes the output to the unit sphere to receive a new n-dimensional feature vector, n being the desired code length. The final two layers simulates a conversion to the -1+1 binary space by relaxing the sine function to a differential operation using a scaled hyperbolic tangent function. So now the output vectors are a floating point estimation of binary vectors. At inference, we can simply use the sine function and get a binary code. But how do we train the network? Our training objective is to preserve the locality when converting the feature vectors by preserving relational distances between data points in the original feature space onto the new binary space. For this, we define similarity scores between items. In the original space, the score is defined as the inner product between two normalized vectors. In the binary space, we define it as the number of locations the two-bit codes are identical divided by the code length. We can call it the normalized Hamming similarity. To formulate the model loss function, we first need to define the Hamming similarity score in a differential manner over a simulated binary space. It can be shown that when the Hamming space is defined as -1+1 over n dimensions, the score can be translated into a function of the inner product divided by n. This now allows us to build probability distributions from the similarity scores in both spaces. For each point, we choose a true k-nearest points from which to build these distributions. Now, we can define our objective as minimizing the KL divergence between the original and Hamming space distributions. However, using the entire training set as reference points to each query in the batch is computationally heavy and prone to overfitting. To avoid this, we randomly sample proxies from the training set at each iteration, so that our loss is formulated only from proxy points. This allows us to faithfully represent the data distribution and generalize the local information. To conclude, we present a method for learning a neural hashing network that maps a large-scale dataset in the feature space to binary codes for efficient ANN. Our method is composed of a simple neural network and a novel training scheme that preserves local relations between data points by translating similarities in the original feature space and the Hamming space to probability distributions and minimizing the divergence between them. We also introduce a simple data sampling method by representing the database with randomly generated proxies used as reference points to queries from the training set. Experimenting with 3 publicly available standard benchmarks, we demonstrate competitive results, achieving improvement of 7 to 17% over other methods. We show good results not only on low but also on high bit codes, bit length, offering flexibility when choosing the balance between accuracy and resources. For further information and references, please read the extended abstract available on the BayLearn site. I welcome your questions and comments. Thank you.